Hello, everyone. This is Dr. Sami from the Biostatistics Learning Group, and welcome to another session here. Okay, guys. So, frequency distributions. Um, One type of table that's commonly used to evaluate data is known as frequency distribution. For nominal and ordinal data, frequency distribution consists of a set of classes or categories around, along with the numerical counts that correspond to each one. As a symbol illustration of this format, table 2.4 displays the numbers of individuals, numerical counts who did and did not suffer from Kaposi sarcoma. Uh, Classes or categories for the first 2,560 cases of AIDS reported to the CDC. A more complex example is in table 2.5, which specifies the number of cigarettes smoked per adult in the US in various years. So to display discrete or continuous data in the form of frequency distribution, we must break down the range of the values of the observation to a series of distinct, non-overlapping intervals. If there are too many intervals, the summary is not much of an improvement over the raw data. If there are too few, a great deal of information is lost. Although it's not necessary to do so, intervals are often constructed so that they all have equal widths. This facilitates comparison along the class. Once the upper or lower limits of each interval have been selected, the number of observations whose values fall within each pair of limits is counted. And the results are arranged as a table. So you have here table 2.4. This is the cases of Kaposi for the first 2,560 patients report to the CDC, yes or no, number of individuals, and this and that. And then table 2.5, cigarette smoke consumption by person aged 18 or older. And here is the year, this is the number of cigarettes smoked per year. Then table 2.6, this is absolute frequencies of serum cholesterol level for 1,067 US male, aged 25 to 34 years, 1976 to 1980. Here's their serum cholesterol level and number of men. So observations range from this and that with relative few measurements at the end of range of large proportion of values falling between this and that. So table 2.6 provides us with a much better understanding of the data that would a list of cholesterol level readings. Uh, Table 2.1 and 2.4, the fact that one kind of information is gained while other is lost holds true even for the simplest dichotomous data in those tables we mentioned. So first we discussed what kind of frequency distribution, and now number two we're discussing not the frequency distribution, but put a word before frequency, which is a relative. So relative frequency. So it's sometimes useful to know the proportion of values that fall into a given interval in a frequency distribution, rather than the absolute number. So it's sometimes useful to know the proportion of values that fall into a given interval, values that fall into a given interval in a frequency distribution rather than the absolute numbers themselves. Okay, so the relative frequency for an interval is a proportion of the total number of observations that appear in that interval. The relative frequency is computed by dividing the number of values within an interval by the total number of values in the table. Alrighty, so dividing the number of values within an interval, so that's why it's relative to by the total number of values in the table. Table 2.7 displays the absolute and relative frequencies of serum cholesterol level. So number of men, relative frequency, number of men, relative frequency. But it's absolute, absolute, and relative frequencies. So you've now we talk about graphs. Graphs are very important. Bar chart. So bar chart, a popular type of graph used to display frequency distribution for nominal, the name to it, or ordinal data. And you have a bar chart here looking at you. And then this is a histogram. And this is a histogram, as you can see. Figure 2.3, where you can see another histogram. And then you've got the frequency polygons, Frequency polygon is absolute frequency of serum cholesterol level for some kind of patients in specific years and a specific age. And it's like a histogram, but it's on a polygon. So frequency polygon. Frequency polygon, relative frequency of serum cholesterol level. Here you got the cumulative frequency polygon, and then you got one-way scatter plots, and here you are. This is a one-way scatter plot. Crude death rates for the US in 1992. Alrighty. And then you got a box plots. So box plots are similar to one-way scatter plot that you saw up here in that they require a single axis instead of plotting each observation. However, they display only a summary of the data, not like the scatter plot. You can see it here, figure 2.8. We have a summary, right? You have a summary of the data, but it's like the one-way scatter plot. By that, it's a single axis. Here you get also one-way scatter plot and a box plot to it. So this is the one-way scatter plot, and this is the box plot. And then you got two-way scatter plots. And then you got line graphs. So here is a two-way scatter plot where you got the forced expiry volume in 1 second, but like versus the forced vital capacity liters. These are the pulmonary function tests in asthmatic patients, and here it's called two-way scatter plots. And here you got a line graph, and this line graph is reported rates of malaria per year in the U.S. from 1940 to 1989. This is the reported case per 100,000 population. This overlaps with Korean veterans returning, Vietnam veterans, and then immigration. Here you got a line graph, healthcare expenditure as a percentage of the gross domestic product for the US and Canada. Alrighty, by this, we'll conclude this session and we'll continue in another session very soon. But we hope that you enjoy this session, and we ask you to follow us on Twitter on this account.